All right. Hey, everyone. Welcome to the Expert Exchange. We're excited to have Finbarr Timbers here today, who's an AI researcher who writes at Artificial Intelligence and has worked at a variety of large research labs, including Midjourney and DeepMind. So, Finbarr, take it away.
Hi, thanks for the intro. Okay, so I'm really excited to be talking to you folks today. I'm going to be talking about one of the lesser known, or sorry, very well known, maybe lesser thought of optimizations that we do, which is batching. As long as I've been, working in machine learning, I've always known, okay, you got to do batches of inference, right? Because in training, because it's much more efficient. But about 2 years ago, I kind of realized that I had no idea of why that was the case. And it never really made sense to me from a first principles perspective, because you're doing more math, and so it shouldn't be free. So I could kind of, if it came up in an interview question, I could kind of fumble through an answer about, oh, GPUs are parallel and do a lot of stuff. So you got to do lots of stuff. But I didn't really have a good understanding of what that was. So I wanted to discover that. So I think I have some answers, and I'd love to share them with you folks today. So, okay, so I mean, batching is a free lunch, and that shouldn't exist. We shouldn't have a free lunch. So why is that the case? Like if we're running a batch of size n, why is it actually, for small enough values of n, like it's the same cost, in terms of wall clock time as running a single example? And I mean, like why is this? I mean, maybe I should start by saying exactly what I mean here when I'm talking about batching and inference here. So when I'm talking about batching, what I mean is that we have some model. During this talk, I'm going to focus on feed-forward networks or MLPs, because they're very similar from a performance characteristic to transformers, which is what the industry as a whole largely cares about right now. And so the idea is that we have some, I'm going to focus on the inference case, and I'm just going to kind of set aside training, although a lot of this stuff applies to training as well. And so the idea is that we have some neural network, and we want to just compute the predicted values using it for some number of examples. And so if we do that with one example, it takes a certain amount of time. And if we do it with 10 examples, it takes a certain amount of time. And typically that's the same time. That's what I mean when I say batching is free from a wall clock perspective. And so that's the phenomenon that we're going to try to understand. And so the first thing that I did is I said, okay, let's do this. Let's take some, I have an MLP here. It's a 10-layer, 1024 dimension MLP. And I just ran inference with it. And it turns out that, yeah, it's not free. The time, increases, basically proportional to the size of the batch. There's some initial setup time, but then it's, a perfect, or at least, noisy line. And so, okay, so I guess I'm wrong. We can just go home, right? The batching isn't an optimization. It's not free. Well, I don't know if you can see my pointer here, but, the important thing to keep in mind is that this is on a CPU. And so it turns out when you're running your inference on a CPU, you can't really do batching. It doesn't see the performance optimizations. And instead, if we run it on a GPU, if we give Jensen Huang a bunch of our money, that we do see this. And so, this is exactly what I'm talking about. As we increase the batch size, the y-axis here is the wall clock time, the x-axis here is the batch size. What we see is that the wall clock time doesn't change, even though we're running, like over an order of magnitude, 30 times more examples through our network. And okay, so why is this? So, well, when we do inference on a GPU, there's a few things that are happening. And so the first thing that happens is you get the weights. They come from somewhere. Maybe they're living in memory. Maybe they're living on a hard drive somewhere. Maybe you download them from Meta if you're using Llama's the Llama models that they've put out, and then you load them onto your into CPU RAM. And so once you do that, you're going to transfer them onto the GPU somewhere, and that's going to happen once. And so I mentioned this just because when I'm talking about memory bandwidth, that's for the rest of this talk, I'm not talking about the initial period where we're loading the weights on the host on the CPU and transferring them onto the device, onto the GPU. That happens once at the start of time, and we never think about it again. Once that happens, we then have to move the weights from the GPU RAM, GPU memory, into shared memory, which is like the on-chip memory. And so we have to do this kind of on an ongoing basis because the on-chip memory is really small. It's kind of hard to get specs for this exactly. The best research I could get is that it's about 200 kilobytes on an A100. Don't quote me on that. I could be wrong, but the point is that it's very small. The amount of memory on the actual chip is quite small. And so when we're actually running inference, we're constantly streaming the weights, the portion of the weights that we need. We're streaming it in and then out of the on-chip memory. And then once we transfer the weights into the on-chip memory, or at least the portion of the weights that we need, we're then actually able to do inference. We're actually able to do math with these weights. And so the beauty of GPUs and the reason that NVIDIA is worth so much money is that we can do these operations in parallel. We can overlap this. And so because of this overlap, we can have a really simplified model of inference time as being the maximum of either the weight transfer time or the computation. So because these happen simultaneously, whichever one of these takes longer is basically going to be the overall inference time. And so the maximum batch size that's free, right, that where we don't incur any penalty for increasing batch size, will be when the two of these are equal. And so the reason for this is that the weight size is fixed, but the computation time scales with the batch. And so we can kind of keep increasing the batch size until we get these two equal. And that's the magic number. And so, for those of you who are more familiar with this, another way of referring to this is the point where we transition from being memory bandwidth bound to being flops bound. That's kind of a common optimization framing for this. And so basically what we're trying to do is we're trying to maximize the amount of computation that we do for every byte that we move. And this is called arithmetic intensity. For a typical feed-forward network, MLP, or for a transformer for that matter, you can roughly approximate it by the arithmetic intensity is basically just equal to the batch size. And the reason for this is just that if you profile a transformer, it's basically just a feed-forward network as long as the context length is small enough for fusing a KV cache. So the way we increase this arithmetic intensity is just by increasing the batch size. And so, if we actually walk through the numbers here, for every matmul that we do, the flops involved from it are equal to 2 times the batch size times the input dimension times the output dimension. So it's 2 times the batch size times the number of parameters. And the basic, I'm going to kind of gloss over this, but the basic intuition here is that for every parameter, you're going to be multiplying it once, you're going to be adding it once. And so that's kind of the high level intuition there. And similarly, of course, for doing this matmul, the weights that we have for that matmul are going to be just the input times the output. And so we're going to call that p, the number of parameters here. And so if we have a feed forward network, this is all we're doing is a bunch of matmuls. We're also doing some other operations, activation function, whatever. But in practice, those basically don't take any time, and so they're not a limiting factor. So we can just ignore them basically. And so with this setting, so we want to find the point where the inference time is equal to the weight transfer time. And again, the inference time is equal to the batch size times 2 times the number of parameters divided by the flops that the chip has. And we want to find the point where this is equal to the time it takes to transfer the weights. And so if we assume 16-bit precision, which is kind of the most common precision level deployed in production, that means that the size of the model is 2 bytes times the number of parameters, because for each parameter we have 2 bytes. And so we'll divide that by the chip memory bandwidth. And so here, and so what's really nice is that means that we have this 2p term on both sides of the equation, and we can just cancel it out. Now, it turns out this is generally true for modern hardware, because at least for kind of the modern NVIDIA hardware, like in H100, for example, as you go from 32-bit precision to 16-bit precision to 8-bit precision, you're able to double the flops for each of those that are available to you at each point there. And of course, as you do that, the amount of memory needed to store each of those models will have in succession. So this ratio is generally true. This isn't always true for older chips like a T4, for instance. That's not true. You kind of top out at 16-bit precision. Don't get any advantage from moving to 8-bit, but this is generally going to hold on modern hardware. So anyway, so we're able to cancel out this 2p term. And so what we get is actually that the batch size, the kind of maximal free batch size, is just the ratio here of the chip flops to the chip memory bandwidth. And that's kind of interesting. To a certain extent, that makes sense. If we have a bigger model, it's going to take, it's going to have more flops, but it's also going to take more time to stream the weights in and out of the memory. So it's kind of nice that those cancel out. Okay. And so, using that equation here, what we get for a T4, right? A T4 using FP16 has about 65 teraflops, 300 gigabytes per second of memory bandwidth. And so we're able to get that we should expect a batch size of roughly 216. That's kind of the magic number that should maximize efficiency. And so then that's kind of the theoretical analysis. And so like any good AI researcher, I'm now going to experimentally verify this. And so I ran a bunch of batches, again with the feed-forward network on a T4 in 16-bit precision, and I got some results. Let's see how it lines up with the theory here. And so this is what we see. So this is the time to run a batch, and it grows exponentially as I grow the batch size exponentially. And what's kind of interesting is it's basically flat for the first bit. And so if I use a different view, if I look at the throughput, so the amount of examples that we're able to process per second, what's interesting is that we see it steadily grow as the batch size grows. And what's kind of interesting is that the place where it tops out and where we start to see maximal efficiency is in the thousands. So from about 2048 onward is kind of where we see maximal efficiency. And so that that's great. We are seeing a point where batch size no longer helps us be more efficient. But what's kind of surprising is that it's maybe 10x the batch size that we would expect. Like, from the analysis we did earlier, we would expect it to be around the 200 mark. And instead, it's about 10 times that. So what's going on there? And so I have this graph here. So this is a bit of a weird graph. And so what it shows is basically the peak, the percentage of the maximum utilization that we've achieved through memory bandwidth and through flops. And so what I've done here is I've normalized our memory bandwidth utilization and our flops utilization to compare it to the peak value that we achieve. So we can basically see where we're achieving the peak utilization here. And so what we see is that we achieve the maximum memory bandwidth utilization. So this is the relative utilization. So maybe we're using 1% utilization, but that 1% occurs at a certain point. So that's kind of what I'm trying to show you here. And then in the next slide, I'm going to show you the absolute utilization. When we look at this relative utilization, what we see is that for memory bandwidth, it peaks quite early, which is exactly what we'd expect. When the batch size is small, we're not doing enough computation. Our arithmetic intensity is too low. And so all of the time is being dominated by memory bandwidth. And so we're able to use, that's where we achieve this maximum utilization. Conversely, as we have our batch size get bigger and bigger and bigger and bigger around that 2000 mark, that's where we achieve our maximum flops utilization. And so we see the memory bandwidth utilization just continues to go down as we are spending more time running the actual calculations. And so again, this red dashed line here, that's that critical ratio, that 216 value that I discussed earlier. And so again, it doesn't quite align, but we can see that that's when we start to see memory bandwidth tank and flop utilization starts to come up. Now, there's still a question though, which is why are we seeing this peak happen at 2000? This still doesn't tell us this. It tells us that we're flops bound, but doesn't tell us what's going on here. And so then if we look at the absolute utilization values, that kind of tells us the story. And so the interesting bit here is that we're actually able to achieve, we're just not really using the flops. And so it turns out that when you're flops bound, sometimes you can be flops bound at a very small number. of utilization here. Like here, we're basically at like 1%, where the memory bandwidth utilization is a lot higher. And so, I mean, if we had more time for this talk, I'm actually slightly over time right now, so I'm going to wrap up right away. If we had more time, I'd try to walk through what's going on here and why we're seeing low utilization. But the point is just that we do see low utilization. Unless we optimize more, it's not going to get better. And that's why our overlap, that's why the maximum batch size is so big. Okay, so some takeaways here. The first one is that batch size matters. There is that we do need to keep scaling the batch size. As we scale the batch size bigger and bigger and bigger, it's going to be more efficient for inference. And for training, which again I didn't really talk about at all here, you obviously have a bunch of gains for better grading updates, more accurate grading updates, that sort of thing. So you also see a lot of gains there. The second is that optimization matters. As you can see here, we're just seeing abysmal utilization, and so even then you're still getting a lot of benefits. But if we could optimize our code better, we'd see it just up to 100x increase in throughput just when we're flops bound. And the last one, and then I'll stop for questions, is that asynchronicity is key. Like as soon as we start blocking, you're gonna see performance tank. We need to be able to overlap these operations so that the data transfer can happen at the same time as computation. Okay, cool. Well, thanks a lot for listening to my talk, and I'd be happy to take any questions now.
Cool. Thanks, Finbarr. I think we have a question on LinkedIn, and it's how do you measure the memory bandwidth?
So I mean, you can do this with Insight, like the NVIDIA. So I assume you're doing this on a GPU. Using well, I assume you don't have to use PyTorch, but you can use whatever framework you're using. NVIDIA's Insight profiler does this for you, and you can measure it there. It's also possible you can kind of approximate it by just tracking how much memory is allocated during certain operations. But you have to be kind of careful there, as sometimes that doesn't necessarily capture everything you need. But yeah, Insight is going to be the best place to do that.
That's cool. Also, another question is, how do you measure, or what is asynchronicity in the PyTorch training loop?
Yeah, I mean, maybe that's a better question for you, Jesse. I actually, ironically, given that I'm giving a talk as part of the PyTorch Expert Exchange here, I've never worked professionally with PyTorch, as I'm more of a JAX guy. So I don't know. That's like, I guess the asynchronicity in JAX, at least, is where you are able to overlap. Like your operations are asynchronous until you actually require a result to be transferred back to the host, to the CPU. And so basically everything happens simultaneously. I assume it's the same for Torch, but
yeah, it's pretty much exactly the same. So asynchronicity in your PyTorch training loop usually comes from host to device syncs. So if you can CUDA graph your training loop or torch.compile it with the CUDA graphs enabled, then you'll get a very fast training loop. Another question from LinkedIn here is, what other important factors would you use other than inference time for large batching jobs in GPU?
Well, I mean, so it depends on the context. Like, so I guess I would say throughput. So like, yeah, it really depends a lot on the context. If you're in a case where, like, let's say you're serving some sort of API, so you're doing like, I don't know, like a language model API, you're serving tokens for like Llama 3 or something like that. In that case, like throughput is going to be the only thing that I would really care about, like the number of tokens we're able to generate per second. There are some caveats there. Like, one way to achieve really high throughput is to shard your model if it's big enough, to shard it over a large number of devices. And so there's going to be like a cost, like a literal like dollars cost trade-off there. But generally, like throughput per second or throughput per dollar is probably going to be the thing that I would care about, and that's going to directly translate to inference time. Typically, as you can directly translate dollars to, or GPU time to dollars. So
yeah, I think I'd add on here too, for like specifically the case of LLM inference. There's kind of two really interesting like steps, right? You have the pre-full step where you're batch size n and you're heavily compute bound, and that affects time, like time to first token. And then when you're decoding tokens per second, you're decoding one token at a time, so you're memory bound. In those cases, like for example, I work on quantization and sparsity, and one thing that we've noticed that's quite interesting is that like dynamic quantization for the prefill step is faster, right? Because you're compute bound. But once you go into the decode step, you want to use weight-only quantization because you're at the memory bound stuff.
Oh, that's fascinating. Yeah, that's a great point.
Yeah. Another question is, as far as I know, there's so much data level parallelism tools in Torch, but is there any option for model level parallelism? I think I can answer this. There's some tools around, I think, like FSDP and DDP that support model level parallelism. Don't quote me on that. I'm not super certain, but I think the PyTorch distributed docs would be a great starting point. And another question, do you have any specific recommendations for profiling optimizations for AMD GPUs? In your personal experience, what will be your top 2 choices for inference? 1, native PyTorch, 2, MLC engine, 3, SGLang, 4, VLM, 5, TGI.
I don't know. I mean, VLM has worked well for me, but I don't. Yeah, I'm not familiar with any other ones other than PyTorch. I don't know if you know. Have any thoughts there, Jesse?
Yeah, we have like Torch.io, which is accelerated GPU inference with just like native PyTorch contracts. We're working on adding AMD support, but I think for like we're trying to partner with like SGLang and VLM too. So I think underlying down the hood, a lot of these implementations share the same kernels, and then the scaling libraries have their own optimizations on top of that.
And actually, maybe one other thing that I will say is that I have had luck when I've tried to run just native PyTorch on AMD. Like as long as you're not doing anything too fancy, it's worked fairly well. So you could also just try it. Maybe that'll work. I'm sure if you optimize it on on a NVIDIA GPU, use their great profiling tools, a lot of that will still transfer over. You actually get to run it on an AMD machine. So.
Yeah, I'm not sure if AMD has specific profiling tools as well, but I imagine they must. Another question is, how do you measure CUDA core utilization? NVIDIA SMI doesn't give this information.
I'm pretty sure Nsight does. Nsight basically has like a ton of really good. It is like every metric you might want. So that's really helpful. I mean, another one, the trick a lot of people use is to look at either temperature of your device or the watts used, because that's pretty proportional to the amount of math that's happening. So that's kind of a good approximation that you can get through NVIDIA SMI. But yeah, like Nsight is basically just the best way to go about all of this.
That's a good tip with the utilization. Another question we have is, how does bandwidth affect data parallel versus tensor parallel for multi-GPU inference?
That's a great question. I mean, so typically, yeah, you're going to use data parallel when your models, like if you're using like standard normal data parallel versus like FSDP, you're going to use that when your models, you have a model that fits on a single device, and you're going to be splitting your batch size across it. So you're typically going to be memory bandwidth bound there because you have a smaller batch size. So in that case, like it's going to be really important. I mean, tensor parallel is you're typically in a flops bound regime there. I haven't run profiling on that recently enough. I mean, I don't know. So yeah, I think in that case you're going to be more flops bound, but it really depends on the specifics. I don't know, Jesse, you probably have more experience with this.
Yeah, I think basically this is kind of like a matmul level optimization. So depending on data parallel versus tensor parallel, you'll be chunking your matmul, and then this is how you speed up that chunk matmul. And I'm sure there's, Amdahl's law. If you're optimizing end to end, you have to figure out what the bottleneck is. But I guess it depends on your situation, is what I'd say.
Yeah, I think it's tough to give a general answer because it's kind of like the answer is to profile, and then go from there. Yeah. So,
with large batch size, the inference time may increase because of collation/padding, whereas small batch sizes result in more memory transfer latency. How should we profile optimize such cases?
So I assume that you're talking about the like large language, kind of like language modeling here, where you might have variable sequence lengths. I mean, that's where first of all, the answer is you should just profile it, see what's going on, and actually work with the profiles that you've gathered. I mean, this is where something like overlapping sequences, where you can use clever masking to put various sequences in together and make sure you're attending to the right ones. that can be really helpful here. It's really just going to depend on the specifics of your situation. I mean, another thing that can happen. So I'm not sure. One interpretation of the question is that like you're talking about variable sequence lengths here. Another one that can happen. I saw this a lot when I was working on TPUs when I was at DeepMind. Is that they're very specific about the exact dimensions of the matmulls that you're doing. I'm sure it's the same on GPUs, but I just haven't run into that in the same case. So you could see, like, you have to have a multiple of 128 in your biggest dimension, and then a multiple of 8 in the second dimension. And so if you do that, everything's fast. If you don't do that, everything's slow. So again, that's a case where optimization can be useful, and just intensively reading the docs and trying to figure out what the exact performance characteristics are. And that's where you might want to use something like some of the frameworks that people like the PyTorch team or that NVIDIA puts out. I don't remember is it Nemo maybe? They recently released a fairly optimized setup that does a bunch of the kind of the weird tricks or the maybe slightly, I shouldn't say weird, but the more obscure tricks. Or, Google has max text, which is again another like highly optimized implementation. You can see a bunch of the memory alignment and some of the more obscure tricks implemented there.
I'd say too, I think some of the frameworks like SGLang and BLM like support continuous like batching. So if you take advantage of those inference engines, you may be able to get this like batch size inference for free. Okay. From a software engineering perspective, how do you make decisions about AI deployment per dollar? How do you decide between A100s versus L40s, or is it just most optimal to go with H100s all the way?
Well, I mean, maybe the biggest answer is that you don't do it from a software engineering perspective. You probably want to do it from a business perspective, right? Where you just see like, okay, what are the actual business needs? How does this impact what's going on there? So, something that I've seen in previous roles has been that if you actually, like, so, one thing you can do is you can spend more money, you use more GPUs, you can shard your models over more GPUs, and latency is going to go down. It's going to be more expensive. Sometimes you do that, and it turns out users don't care, or they might actually say if your latency is too low, they might think that your model is bad, and then it's not thinking long enough or whatever. And so I would just say that you should really try to get an understanding of the business needs and kind of how that impacts your end metrics, and then try to find the most cost-effective way to do that. I mean, one of the ways that in the past that I've chosen kind of CapEx allocations for GPUs is just to look at like flops per dollar and to say like, we know to deploy our, for our production inference stack, we need at least like, 50, gigabytes of GPU memory. And so then, you say, okay, now then looking at all of the GPUs that have at least that much memory, like, what's going to be the most performant per dollar? And then you kind of make the decision in that sense. But again, it's really going to depend on kind of nailing those business use cases and then trying to see like, which setup is going to help you there. And I mean, lately NVIDIA has really helped us make this decision because it's been impossible to get many types of GPUs. And so we're limited to whatever, Jensen will provide. So.
Perfect. Another question is, do you have any specific recommendations for batching on smartphones?
I don't. I'm not actually at all familiar with local inference.
Yeah, I don't either. But I think the theme of this Q&A has been profiling. I think the hardware-specific sort of memory, the critical PAT ratio, I think that Finbarr was describing is probably specific for your...
Yeah, calculating arithmetic intensity, figuring out that critical batch size, and then just, but again, profiling is the best answer.
What are your favorite profiling tools to monitor batching?
Well, I would say I don't really have favorites. It's kind of like whatever they'll give me. And so, that's basically Insight. I mean, when I worked at DeepMind, they had a bunch of great internal tools. And I no longer work there, so I no longer have access to them. But Google had really great internal profiling tools. But Insight is great, and it really does everything that I need. I mean, something I like to do a lot is to you can output it in the I forget the exact name for it, like the .viz framework. You can get like a profile, and you can break it down into the call stack, and then you can output it in the dot file format, and then you can visualize it. I found that really helpful to actually visualize where the you can visualize with graph is, and then you get like a nice little like HTML page that you can like zoom in on and explore. And I found that to be really helpful when I'm doing optimization work. But often in my experience, you have a really obvious bottleneck. And so again, if you do any profiling, if you use any tool, you see a big red box that says, oh, this is 99% of your time, and then you're able to optimize it. And particularly as we get into more kind of obscure use cases, or not even obscure, but like I was doing JAX on GPU a few months ago, and there was like no profiling tools for that basically. And so it's just it's whatever you can get.
Yeah. Another question is, does PyTorch dispatch to different cuBLAS functions / Triton curls depending on problem size? Would we do a GemV dispatch to tensor cores anyways? Yeah, I can answer this question. I think we've recently added some inductor templates. So my understanding is that for batch size 1 decode, we're doing that like as a sum prod, so not using tensor cores. I think this is kind of like a work in progress and something we're looking into currently. What techniques can be used to overcome limitations caused by insufficient memory for large batch sizes?
Yeah, so one option, so it's various sharding mechanisms. If you look at the movie gen paper, actually from Meta, it's a really great example. I don't work for Meta; they're not paying me, but it's a great paper, and it covers basically every sharding. They use just an incredible array of sharding techniques there, and that kind of covers all of them. So I'd kind of go through all the sharding techniques they use, and it's going to depend on your situation, which ones are going to be relevant to you. I mean, the obvious one is going to be the stuff that's come up so far, which is data parallel, FSDP, which is fully sharded data parallel, and then some sort of model parallel approach. Those are, or tensor parallel. Like those are kind of the three main ones, and they cover most of your use cases. But it's really going to depend on exactly where the memory problem is and what the exact use case. Like for inference, I guess you can do data parallel, but you might be limited by batch size, whereas maybe some sort of FSDP or tensor parallel or something will be more helpful there.
Yeah, I think also you have like techniques like quantization and sparsity. You can use those to shrink your bit width or reduce the number of parameters you're doing your matmul with to increase your batch size. Another question about profiling, this time for MPS. Any tricks for MPS profiling?
I'm not familiar with MPS, so yeah, I don't know.
Yeah, unfortunately, I haven't done much work with MPS either, so sorry. Cool. Well, I think this is most of the questions. Thank you, Finbarr, for taking time today to come speak to us, and thank you everyone for coming to attend and ask questions.
Yeah, thanks for having me. This was fun.
Yeah, that's great. All right.